I don't do it, please remind me. Okay.
Sure, sir.
Yeah. All right. So uh, we introduced about the need of digital electronics in the last class. So today we'll start with the first topic, which is your number systems. When you take any number, right? Say for example, uh, if you take a number, say for example, say 5, right? This particular number, actually it has got a base. Base in the sense with what this particular number is being made. So this particular number, we know that this is a decimal number system, right? When we say decimal number system, what does it mean is your decimal number system, it varies from 0 to 9. And after 9, what happens? After 9, again, these numbers repeat themselves. Repeat themselves in the sense after 9, we get 1 0. After 1 0, it is 1 1 1 2. Likewise, it repeats itself. So which means any number system you take, we have taken an example of a decimal number system here. So any number system you take, they will have a base. Base in the sense the number of digits that are possible in decimal is here it is 10 digits. So and other thing that you have here is in addition to base, you have symbols also. Symbols in the sense, say for example, this is a symbol. This is a symbol. These are symbols, right? So and we are calling them as 1 2 3 4 5 etc. So now if you consider the different kinds of number systems that you have, the basic number system that we know is the decimal number system. In case of a decimal number system, we know that its base is actually 10. What do you mean by its base is 10? It means that from 0 to 9 we have got 10 different symbols. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So we have got 10 different symbols. And what are those particular symbols? So that is what is mentioned here. So the symbols are 0, 1, 2, 3, 4, 5, 6 till 9. So just to make how what we interpret and what the machines interpret, decimal number systems, we interpret it much better, right? Yes, we do interpret it. Does computers know that this is a number system? They do not know that this is a number system. Next kind of a number system, if you look, the binary number system. When I say a binary number system, it means that either its base is 2. When I say base 2, it means that in that particular number system, number of symbols that are possible is only 2. Right? There are 2 symbols only is possible in case of a binary number system. So that is why it is called as a bi. Bi means 2. So what are those particular symbols? It is 0 and 1. They are the symbols of a binary number system. So similarly, there is octal number system and hexadecimal number system. You all know what is an octal is. Octopus, right? It has got 8 legs. So octal, it has got a base of 8 and the symbols that you have is from 0, 1, 2, 3 till 7 only. If you take hexadecimal number system, so in case of a hexadecimal number system, hexa means you know that it is a 16, right? Hexa means 16. It means that hexadecimal number system has got 16 symbols. When we say 16 symbols, what are the possible symbols? We know the decimal has got 10. So 0, 1, 2, 3, 4. And then let me write here 5, 6, 7, 8 and 9. After if you write 10, then it means that you are repeating the same decimal number system only. But it has got your hexadecimal system has got unique 16 symbols. So 10 symbols are already here. What are the rest of the 6 symbols now? Rest of the 6 symbols, after 9, we follow alphabet A, alphabet B, alphabet C, D, E and F. So these are the 16 numbers, 16 symbols that we use in hexadecimal number system. Now coming to what is what we interpret and what the human interprets. Do we follow a binary number system? Obviously no, because binary number system, it has got zeros and ones. Do you understand what is this particular number equal to? We don't understand, right? So we do not use the binary number system. Do we use octal number system? We do not use octal number systems also, as well as hexadecimal number system. Whereas your computer or the machines, they out of these four different number systems, they understand only the binary number system, that is ones and zeros. So that is the reason all your digital systems are the one that we are going to incorporate inside our machines. We are using binary number system and not any other number systems. And in hexadecimal number system, we use alphabets A, B, C, D, E, F, right? So what is equivalent decimal value for these A, B, C, D, E, F is after 9. If it is a decimal number system, we could have written 10. Since we need 16 unique symbols after 9, we started using alphabets. So A is equivalent to 10, B is equivalent to 11, C is equivalent to 12, D is equivalent to 13, and E 14, and F is equivalent to 15. Right? So now coming to the digits, because if say for example here, I have written so many digits here. These digits are very, very important because they will decide the capacity of the handling of your machines. As a human, how many digits can you handle? We can handle infinite number of digits. As a computer, it has got a limitations of how many digits that you can handle. Say for example, in 90s, if you look, the processors that we had were called as 4-bit processor. The 4-bit processor, the 4-bit computer, in fact, which means that it can process only 4 bits, 1011 example, 1100, this is some example, only 4 bits it can process. Then we got 8-bit processor, then we got 16-bit processor, then 32-bit, 64-bit, 128-bit, 256 bits. And what is the thing that we are having now? If you look my system 2, let me open it, is my PC. If you look at the properties, you look at this particular property, it is a 64-bit operating system. So which means that as I move my mouse here, or if I am saving something, or if I am editing something, I am processing in a 64-bit operating system. It means that anything that I do is represented in 16 bits. So that is what is the importance of the digits actually. So if I have 3 digits, then this is an example of a 3 digits. So 259 is an example of a 3 digits. So the maximum I can have is 999 is the maximum digits that I can have if I am using a 3-digit processing machine. So this is in terms of decimal. This is in terms of decimal. Similarly, in case of a binary system, we have got 8-bit processor, 16-bit processor. Just I showed you that it is a 64-bit processor. When I say 64-bit processor, it means that my system can handle maximum 111111. Likewise, 64 ones is the maximum bit that is possible. Now, as humans, as we have just seen now, that we do not interpret the binary number system. Only machines can interpret the binary number system. So what we do here is, but we must understand, if we are designing something, we must understand what is the 64 ones are equivalent to. So what we do is, we convert these binary numbers to any other number system. I can have, okay, I am unable to write. So I can convert this into any other number system, any other number system. Okay, now immediately, since we are seeing here, there are different bases possible, right? So and as a number system with 2 base is possible, a number system with 8 base is possible, 16, 10 are possible. Why these numbers? Why we have got 2, 8, 16? Why not we have a number system having, say for example, 3 with bases 3? Is it possible? My simple question to you is it possible to have a number system with base 3? Is it possible to have a number system with base 1? Is it possible to have a number system with any number of your understanding? So for example, can we have a number system with 6 as a base? Is it possible? The answer to this particular question is yes, it is possible to have a number system with any base number. So which means a base number with a system of 1 is also possible. When I say if a number system with 1 is possible, then what are the, how many symbols a base system with base as 1 is possible? Is definitely it is possible. If base 1 is possible, then how many symbols then? So there can be only one symbol possible, right? That particular symbol can be either 0 or it can be 1 or any symbol you can choose. You can even choose as 8, you can choose as even 6, or even you can choose this number system as say some alphabet also, say K, right? So with this particular K you can operate. But if you choose that particular symbol is 1, then how do you represent 5? If I want to represent 5 in a base system with a number system with bases 1, this kind of number system with bases 1 is called as a unary number system. It's called as unary number system. The number system with bases 2 we call it as binary number system. The number system with bases 1 we call it as unary number system. Okay, in unary number system we have chosen that our symbol is 1. Then how do I represent the decimal value 1? I will represent the decimal value 1 as 5 times 1 in unary number system. If I have chosen my symbol to be 1. If I have chosen my symbol to be K, then 5 can be represented as 5 times K. So this is also a unary way of representing 5. So, but then why are we not using one number system? Why are we not using one number system is because they are practically not possible to implement, right? So that is the problem here. So that is the disadvantage with this unary number system. Now let us count. Let us count the different decimal number systems. Though I have written here, it is always better that I write it one more time for you. What are the decimal numbers that are possible? Decimal numbers that are possible are 0, 1, 2. I'm going to write slightly longer number of numbers. Till if I can type also. Yeah. Okay. Is it possible? This is the table. Okay. Okay. It's better I write here. So 6, 7, 8, 9, 10. Okay. This is decimal number system. After 10, what we are doing? We are going to repeat our symbols, right? So it is 1 and 1. The least significant bit, it changes, right? What is the least significant bit? This one, the ones number, the ones position, right? So they changes actually. The tens position doesn't change. When does tens position changes? After my ones position completes one cycle, my tens position changes. So it is 1, 1. Then it is 1, 2, which is 12, 13, 14, 15 here, 16, 17, 18, 19. After 19, then this repeats, right? 9. After 9, we have got a symbol 0 only. Then this 1 gets implemented. Then we got 2 0. So 21, 22. Yeah. If required, we can have one more, which is 23. Now, in binary number system, how do we represent? in binary number system, we represent 0 as 0. We represent 1 as 1. We represent 2 as, we are exhausted with our symbols now. Then what we do? We add additional symbols to the left hand side. So it is 1 and 0. And now what happens? This least significant bit, which is the least significant bit, this is the least significant bit, it increments. So we have 1 and 1. After this, we are exhausted with two bits. We call each digit as a bit here in binary number system. So we are exhausted with 2 bits. Then what we do? We go in for 3 bits. So what gets incremented? I will add one more digit here to the most significant place, and then these ones gets replaced with 0 0. Now what happens? 1 0 remains and this one gets incremented. And then what happens? This gets incremented and this gets reset. So likewise, you can fill the binary number systems here, 1 1 0 and then 1 1 1, and then you have to add 4 bits for now. It is then again it repeats this process, 1 0 0 1 1 0 1 0 1 0 1 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1, and then again now we have from 4 bits we are going to 5 bits now, 0 0 0. We have got 5 bits now. So what is the equivalent value of 17? It is 1 0 0 0 1 1 0 0 1 0 1 0 0 1 1 1 0 1 0 0 1 0 1 0 1 1 0 1 1 0 1 0 1 1 1. So this is how the equivalent binary bits are formed from decimal values. So if you see here, where are the changes that we are doing? Changes in the sense we added, there was a 1 0 that is from 9. We added one more bits to change it to 1 0. Similarly here also, we first added one more bit here, 1 0, and then we added third bit after we are exhausted here. Then we added fourth bit after we got exhausted with 1 1 1 1. After we got exhausted with 1 1 1 1 1, we added one more bit here. So likewise, let us look at the octal number system. In case of octal number system, again, we have got, what are the symbols that we have? Our symbols are 0 to 7 are our symbols. So it is 0, 1, 2, 3, 4, 5, 6 and 7, right? After 7, we are exhausted with our symbols here. Then it repeats as 1 0, 1 1 1 2, that is 12, 13, 14, 15, 16, 17. Now we are exhausted with our symbols again. So now what happens is after 17, my 1 gets incremented to 2 and 7 gets reset to 0. So it is 21 now, 22, 23, 24, 25, 26, 27. After 27, that is 24 decimal value is equivalent to 1 1 0 0 0 in case of binary, and in case of octal it gets reset to 3 0. So where are the reset taking place here? Reset is taking place here, 3 0. Reset is taking place at 2 0 here, and again reset is taking place here at 1 0. Now similarly, hexadecimals, we have already written the symbols. What are the symbols here? It is 0 1 2 3 4 5 6 7 8 and 9. Our symbols are till 9 only, and then we will have A B C D E F, right? So we have A here, B, C, D, E, and F. After F, what will happen? After F, then if F gets reset to 0, we have to add one more digit here, then that digit is 1. Then after 1, it is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, and 1, 8. I mean, if I continue this particular thing, just for your sake of your convenience, it is 1, 9. After 1, 9, it becomes 1A, 1B, 1C, 1D. Let me, okay, 1D, 1E, and 1F. After 1F, it gets reset to 20. So where are the resets taking place? It is at this particular place, 20, it is getting a reset. At 10, it is getting a reset, right? So this is how the number systems and the equivalent values are in fact written here, right? So this is the same thing. Now, normally as humans, what we do here is we understand only decimal numbers. We are very much, because we have been using this decimal number systems from our very childhood, so we can remember, or we can visualize the decimal number systems much better when compared to any other number system. So, but computers understand only binary number system. There were machines which were developed in early stages of 1970s and 60s, where machines that operated in octal number systems were used. Machines that operate in hexadecimal number systems were used. So, but those particular machines did not thrive upon for any upgradation that were required. Their hardware requirements were much complex, so hence they did not sustain. So, so the machines which handled binary number system sustained, and we are still continuing to use the binary number system. But if as humans, if we are designing a binary number system, we must always, when our thinking process starts, we will think in a decimal number system, then we convert it into a binary number system. And then say, for example, if you're having a machine with octal or hexadecimal number systems also, we must have the capability to convert from decimal to octal, or octal to hexadecimal, or hexal to binary, or all these conversions must be possible, right? So based on that, you can always have a conversion from one number system to other number system, which means that if you are having some numbers in decimal, you can easily convert them into binary. If you are having anything in binary, you can easily convert them into decimal also. Likewise, conversion between binary to octal and octal to binary is possible. Conversion between decimal and octal is also possible. Likewise, between hexadecimal also, it is possible for conversion between all these quantities. Please note that these four are not the only conversions, not the only bases that are available. You have unary binary system. You can have a binary system with base 6 or 7 or 8, or 8 is already there. Even with 5 you can have. So all these conversions are definitely possible. But now, okay, if the conversion is possible, is it easy? The question is, it is easy, but you have to follow a certain process. What is that particular process is? Say for example, you are having a decimal number system. From decimal number system, converting it to a binary number system is very much straightforward. Similarly, from binary system, converting it to octal is straightforward. Converting it to hexadecimal is also straightforward. But in case you want to convert from decimal to octal binary system directly, it is not possible, right? Then what you should do is, first you must convert to binary and then to octal. Similarly, it is not possible for you to convert directly from decimal number system to hexadecimal number system. So what you have to do is first convert them into binary, and then from binary you have to convert it into hexadecimal number system. So direct conversion from decimal to hexadecimal and decimal to octal, it is not possible. So now how do we represent this? How do we represent this is, okay. Now let us look at the conversion. We are looking at the conversion of one number system to other number system. Let us say, for example, I am having a number 25, right? Now, how do you know that this particular 25 belongs to decimal number system, or obviously it is not a binary number system? Yes, because binary has got symbols ones and zeros only. This 25, it can be either a decimal number system or it can be an octal number system, because we have symbols 2 and 5 in octal number system, or you do not know whether they belong to a hexadecimal number system, right? Now, how do we identify it? So in order to identify, always, whenever you write a number, we will write their base at the bottom as a suffix to this particular least significant number or the ones position. So if 25, if I represent that this is a decimal, this belongs to a decimal number system, then I always write that the base of decimal is 10. Okay. And if, say, for example, this 25 belongs to an octal number system, then all I do is I write its base as a suffix like this. If this belongs to a hexadecimal number system, all I do is I write 25 and then I write 16, representing that this 25 belongs to a hexadecimal number system. Now, how is the conversion possible? How is the conversion possible is 25, right? So we have this particular table, right? So 25, what this corresponds to? It corresponds to 11001, right? So this 25 in decimal number system is equivalent to 11001. Please note that again ones and zeros are a part of a symbol of decimal, octal and hexadecimal. So there can be a decimal number also. Say 10 is a decimal number. It can be a binary number. It can be a octal number or hexadecimal number. You see in this particular diagram, we have 10 everywhere. We have 10 here. We have 10 here. We have 10 here. And we do have 10 here also. Right. So we have to first identify what kind of number system is this. So 25 to the base 10, which is in a decimal number system, is equivalent to 11001 to the base 2, representing that this is equivalent to a binary value of 11001. In terms of octal, what is that it is equivalent? In terms of octal, it is equivalent to, it is 3, then it gets reset to 1. It is equivalent to 31. And how do we know that this is octal? We write as base 8. Then what is the equivalent hexadecimal value? The equivalent hexadecimal value is, this corresponds to 17, 18, and this corresponds to 19. So 19 to the base 16 corresponds to the equivalent value of 25 in decimal number systems in hexadecimal is what is 19 is. So as I said, this 10 is your base. This 10 is your base, 2 is a base, 8 is a base, and 16 is a base. Similarly, one more example, if you take 16 to the base 10, which means that this is a decimal number system. If 16 is a decimal number system, then what is its equivalent binary? It is 10000 is the binary, and 20 is your octal representation, and 10 is your hexadecimal representation. So 16 10000 to the base 2 is a binary representation, 20 in octal representation, and 10 in hexadecimal representation. Now let us look at the decimal number system. Right. Now, as I said, this conversion, if you want to do this conversion from one system to other system, that is at least from decimal number system to octal number system, first you must convert to binary and then you have to convert to octal. Similarly, if you want to convert from octal number system to binary number system, you cannot do it directly. Instead, you have to convert to binary and then from binary to decimal you have to convert. So now let us look at slightly in detail about the decimal number system, because once we know decimal number system, then your hexadecimal number system and octal systems are slightly easier to represent. In case of a decimal number system, what are the symbols that we have? So the symbols that we have in decimal number systems are, we have from 0, 1, 2, 3, 4, 9. So we have 10 different symbols. It is not numbers, it's actually symbols. Okay, so its base is 10, which or we can call this particular base or as 10, or even we can also call them as a radix. Okay, now these depends on the digits that we are writing here. Say if I write that 239, these digits are each digit that we are writing here, 2, 3, 9, they have some kind of a weight. What do you mean by weight is, these are called as positional weights. That is, based on their position, they will carry a weight. What does it mean is, it means that this 9, the position, this particular position, it is called as ones position. Sorry, ones position. This position is called as tens position. This position is called as hundreds position. Right? So which means that this 2 corresponds to a weight of 100, 3 corresponds to a weight of 10, and 9 corresponds to a weight of 1. So based on that, any decimal value can be represented something like this particular table. Maybe I'll redraw this particular part. If I'm having a decimal number system, I can have, say for example, this decimal number system, either it can be a whole number or it can be an integer number, right? Or it can be a fractional number, right? Or decimal number. So which means if I have a decimal number, then I will have some digits to my left and some digits to my right of my decimal point. If, say for example, my decimal point is somewhere here, this is my decimal point, then say 235, 2356, I will have some numbers to left of my decimal value, and 5, 4, just random numbers. I will have some part to the right of my decimal values. This particular portion is nothing but your integer portion, called as an integer portion, and this particular portion is called as a fractional portion. And what is the weight? What is the weight of this particular, these positions are? The weight here, I'll just this also has come, don't worry about it. So where do we have our dot? We have our dot exactly in the center. And what is the weight of 6? Weight of 6 is, normally it is represented as 2 power 0, right? Or since its base is 10, since this particular base is 10, we know that this is ones position, right? This is ones position, this is tens position, this is hundreds position, and this is thousands position. Likewise, it will keep on going. Similarly, on the right hand side, this position is 1 by tens position, 1 by hundreds position, 1 by thousand, 1 by 10,000s, 1 by a lakh position, right? In short, instead of 1, 10,000, 10,000, likewise, instead of adding zeros, what we used to do is, we know that for a decimal sum number system, base is 10. This is our base. So it is actually, what is 1? It is 10 power 0, right? This position is called as a 0th bit position. This is first bit position, second bit position, and third bit position. So it is 10 power, 10 is represented as 10 power 1. 100 is represented as 10 power 2. 1000 is represented as 10 power 3. Similarly, here again, it is 1 by 10, right? So it is 1 upon 10, 10 can be written as, this can be written as 10 power minus 1, 10 power minus 2, 10 power minus 3, 10 power minus 4, and 10 power minus 5, etc. So this is how we represent the digits. And the first most digit that you are encountering here in this particular box, this is called as the most significant bit. This is called as the most significant bit. And the last bit that you are having somewhere here is called as the least significant bit. In case of decimal number system, it is not bit, it is a digit. So it is digit. And in general, how do you write? Since this is a digit, it may be true for octal number system or even for hexadecimal number system, right? So in case, if it is a octal number system, then in case if it is an octal number system, then what do we do here is, so this will be the decimal value, and what will be the weight of this position? The weight of this position is going to be 8 power 0, 8 power 1, 8 power 2, and 8 power 3. This will be 8 power minus 1, 8 power minus 2, 8 power minus 3, 8 power minus 4, 8 power minus 5. Likewise, it will go on. So in general, since in decimal, octal, and hexadecimal, we call each base as each one as a digit, in general we can write it as d power 0, d power 1, d power 2, d power 3, dot d power minus 1, d power minus 2, d power minus 3, etc. Now these are the positional bits, right? Positional weights. These are nothing but the positional weights. These positional weights, if say for example, if you want to get the actual value of it, then how are they represented here is, the digits are multiplied with their positional values. Say for example, here we are having some digits called as D0, D1, D2, likewise, etc. Then we multiply them with the positional weights in order to get the actual value. In general, they are represented as like this. So D0 here, you can see here that it is multiplied by the positional weight 10 power 0. D0 is multiplied by the positional weights 10, 0. D1 is multiplied by 10 power 1. So D1 is multiplied by 10 power 1. Similarly, on the right hand side, the fractional part section, D power minus 1 is multiplied by 10 power minus 1. Likewise. So let us take a simple example here. It is 3518.53, right? So 3518.53. How do I represent in terms of decimal positional weights? So it is 3 multiplied by, what is the base of it? Its base of it is 10. And what is the position of this? Position of this is 3. Similarly, 5 multiplied by 10 power 2 plus 1 multiplied by 10 power 1 plus 8 multiplied by 10 power 0. Now the fractional part here, dot 5 multiplied by 10 power minus 1 plus 3 multiplied by 10 power minus 2. Now what is this particular value? 3 into 10 cube is 1000, so 3000 plus 5 into 10 power 2 is 100, so it is 500. 1 into 10 power 1 is 10, so it is 10. 8 into 10 power 0 is 1, so it is 8 dot. It is 5 into 10 power minus 1 is 5 divided by 10, which is 0.5, sorry, plus 0.5 plus 3 by 100, so it is plus 0.03. 3 by 100 is 0.03. Now when you add all these things, you will get this same value. It is 3518.53. Right? So we have got this particular decimal value. So this is how you will write the decimal equivalent in terms of positional weights. Now all these are positive numbers, right? Say for example, this is a positive number. 303,518.3 is a positive number. But compute in case of negative numbers, if you want to represent negative numbers as human beings, we know that, say if we write minus 54, then we know that this is a negative number. Normally subtraction, computer, how does it do subtraction is, they do not do subtraction as we do as humans. Computers will do subtraction by adding. They will follow a method of addition to do subtraction. Slightly confusing. So what do I mean by that is, say for example, I want to subtract this number 100 minus 54. Instead what we can do is, this 100 minus 54 can be written as 100 plus minus 54. Am I right? Which means what is that we are doing? So this is a subtraction. But here what we are doing is, we are performing an addition with a negative number. So that is the difference. Even your computers will not do subtraction, but they will do addition with a negative number. So what we should do is, we should convert this negative number into an equivalent positive number. That is called as the complement number, right? We call this converting this negative numbers into an equivalent positive number. We call them as a complement numbers. There are two different types of complements of any negative number. If you want to represent as a positive quantity, then there are two ways of writing the complement number. One is the nines complement. We call them as a nines complement, and other we call them as a tens complement. I will come back to this nines complement later. Before that, what is the tens complement? Tens complement is nothing but nines complement. You take nines complement and add 1 to it. 9 plus 1, 10. Why we are not doing this, I will explain when we do an example. So you take a nines complement and add 1 to it, you will get a tens complement. Now coming to nines complement, let us take an example here. Say for example, as mentioned here, let me go through the notes here. Subtraction of a binary numbers can be accompanied, not only binary numbers, even decimal numbers. Yeah, in case of computers actually. In case of computer, subtraction of a binary number can be accompanied by ones and twos complement. Please note here that I said that nines and tens complement is for decimal number system. For a decimal number system, what is the base? Our base is 10. That is the reason you are having nines and tens complement. Your binary number system, its base is 2. That is the reason you have two complements of a binary number system, which is 1's complement and 2's complement. Similarly, if I ask you for an octal number system, what are the complements that are possible? Octal number system's base is 8. So the complements that are possible are 7 and 8. For a hexadecimal number system, your base is 16. So what are the complements that are possible? Anybody? Anybody? What are the complements that are possible for a
15
hexadecimal
and
number?
16.
Exactly, 15 and 16. One more, anybody else can answer. If I have a number system with base as 5, what are the complements that are possible? Last question.
4 and 5.
4 and 5, right? All right. Now, what is important to us? What is important to us is this decimal number system is important to us because this is what we understand. And binary number complement system is important to us because this is what computer understands. So we have to study what we understand and what computer understand. So that is the reason, as far as this particular chapter is concerned, we will be doing 9's complement and 10's complement and 1's complement and 2's complement for binary. As mentioned here, subtraction of a binary number can be accomplished with 1's and 2's, but we will see this 1's and 2's later. Okay, now we will start doing for a decimal number system first. Now say for example 1 2 3 5. I am going to represent the 9's complement of 1 2 3 4. How do you write the 9's complement? 9's complement means the equivalent complement number of this 1 2 3 4 which can be added, right? If I want to perform, say for example 5 4 6 2 minus 1 2 3 4, if I want to perform this subtraction, then first I should do 5 4 6 2 plus minus 1 2 3 4. So how do I represent the complement of minus 1 2 3 4 is what we are going to see. So the 9's complement of 1 2 3 4 can be done as simply by subtracting 4 9's with 1 2 3 4. So subtraction is straightforward, right? 9 minus 4 is 5, 9 minus 3 is 6, 9 minus 2 is 7, 9 minus 1 is 8. All I should do is I should add, here I am performing an addition only, right? I am performing 5 4 6 2 plus. So I will be performing 5 4 6 2. I will be adding with 8 7 6 5. What does it mean? It means that the equivalent complement of minus 1 2 3 4 is 8 7 6 5. I will have to add this. You will have doubt. You will get a reminder, right? Where I am going to tell you that. Now, when you add this, what will happen? 5 plus 2 is 7. 6 plus 6 is 12. Remainder 1. So it is 5. It is 2. Remainder 1 9 14. Right? 1 4 2 2 7 is what the answer we are getting. Now let us directly subtract and see. 5 4 6 2 minus 1 2 3 4. If I directly subtract, how much it is? 4 6 8 8 or 7. Yeah, it is 8. Okay, so remainder 1 is 2, and then yeah, remainder is 2 here, and then it is 4 here, right? So you compare the actual solution. You compare the actual solution here. This is the actual solution. By adding, what is that we are getting? 4227, but we are getting 4228. So the rule says that if you are doing such a complemented addition and if you are getting a remainder 1, you add this 1 towards the least significant position. So 7 plus 1 is 8, 2, 2, 4. So this is how you will perform a complemented addition, right? So this is how we get the actual results. Instead of doing subtraction, we get by doing addition, right? So the complement of 1235 is 8765. Complement of 826.27. What we need to do? All we need to do is simple subtract them from 999.99. So that we please note, we are doing 9's complement. I will tell you what is a 10's complement is. So it is easy for you to subtract from 9, right? Only if you have a 10, then the carry forward and all those issue will come. So it is easy for you to subtract. Similarly, what is the 9's complement of 3250.705? All you need to do is subtract it from 999.999 minus 3250.705. So I mean, don't look at the answer here. We will do it. So it is easy, right? 9 minus 5 4, 9 minus 0 9, 9 minus 7 is 2, and 9 4 7 and 6, right? 6749.294. So this is how you perform the 9's complement. Now still 2 more minutes. Okay, maybe, yeah, I'll complete the 10's complement and then we may wind up. So what is the 10's complement? I just said you now that 9's complement is 10's complement is nothing but 9's complement. You perform 9's complement, and whatever the answer you are getting, add 1 to it, right? Add 1 to it. So what you get is 10's complement. Am I right? So that is what is performed here. I'll show you the solution here. Yeah, I'm going to perform the 10's complement of 3426. First, what is the 9's complement of 3426? It is 9999 minus 3426. It is 3, 7, 5 and 6. 6573 is the 9's complement. And if you want to get 10's complement, all you need to do is add 1 to it. So it is 6574. You have to add here. So this is what is your 10's complement is. Take one more example here. What is 10's complement of 267.805? First take 9's complement, 999.999 minus 267.805 is 4. 9, 9 minus 1 is 8, sorry 8, 9 minus 8 is 1, 9 minus 7 2, 9 minus 6 3, 9 minus 2 is 7. And then add 1 to it, what you get is 732.195. So this is what is your 10's complement is. So we will do how to really perform subtraction using this 9's and 10's complement in the next class. Any doubt so far? You want me to repeat anything? Any doubt?
So in the last example,
Yeah, please. Yeah, please. Go ahead, Rahul. Rahul, please go ahead.
so in the last example that you explained,
Yeah.
we have to add 1 after the decimal.
Yes, always to the least significant bit.
Okay.
Always, yes. Rahul's question is, which is very, very valid and correctly pointed out question here. You have to, please note here, you are adding 1 to the least significant bit here. Similarly, though you have decimal here, you have to add 1 to the least significant bit only. And don't add 1 here. You should not add 1 here. Okay. So it's a very, very valid observation here. So you have to always add 1 to the last bit position only. Yeah. Yeah. Somebody else was also asking doubt.
No, sir, I had the same doubt.
Oh, okay. Good. Yeah. So any doubts? Okay, great then. So next class we will start our, we'll continue with the 9's complement and then more on number systems. And you can expect the tutorial sheet to be placed on the blackboard, but I don't expect you to solve. Okay, so this particular week you are free. Don't do any job. We will start everything from next week. But however, you will have a tutorial sheet posted, and we will discuss the tutorials, and then maybe you can do the tutorials. Okay, then thank you so much, and let's meet on Monday.